In our lab, we're going to take an engine through the following cycle. We'll start at state A and go to state B via an isothermal compression. Then we'll go from state B to state C via an isobaric expansion. From state C to state D via an isothermal expansion. And from state D back to state A via an isobaric compression. This is a closed loop cycle that you will be executing during the laboratory. You will collect pressure, volume, and temperature data for each of these 4 states. You'll input this data into a spreadsheet, calculate the amount of work done, the amount of heat input, and finally the efficiency of this engine. Okay, we're going to set up a Microsoft Excel spreadsheet to be used to calculate the efficiency of a heat engine. I highly recommend Microsoft Excel over Google Sheets because Microsoft Excel actually can do a lot more. Plus, you have free access to it. Let's create the following column headers. Righty, here goes. PVTN, thermodynamic energy state A, B, C, D. Underneath PVTN, let's create the following. P for pressure, V for volume, T for temperature, N for number of moles, and then underneath N for number of moles, enter the following. PDA, comma, AVE, colon. Let's do a little formatting here. Highlight the DA, comma, AVE, not the colon. Right-click on that highlighted text, choose Format Cells, and select Subscript. Move over 2 cells and type in the following. PBC, comma, AVE, colon, and highlight the PBC, comma, AVE. Right-click on that highlighted content, Format Cells, and Subscript. Using a pressure sensor and capstone tools, we figured out that the average pressure between thermodynamic energy state D and A was 98,657. Enter that. That comes from a pressure sensor, so the pressure at A is going to be the same as the pressure at D because we're using an average value. We are going to consider the pressure at state A to be the same as the pressure at state D. So for the pressure at state A right here, let's just enter equals and then click on PDA average because once again, the pressure at A will be considered to be the same as the pressure at D and we will just take an average value. There. The volume at thermodynamic state A is going to come from a rotary motion sensor, and let's just enter that right now as 1.6139 times 10 to the minus 4th cubic meters. The temperature at state A comes from a temperature sensor, and let's enter 276.7491 Kelvin. Again, that comes from a temperature sensor. Let's use the ideal gas law to compute the number of moles of working substance in our engine. If PV equals nRT, then N equals, ready, equals P, click, times V, click, divided by T, divided by R, which is 8.314. Here's our first sanity check. You should have exactly 6.920035 E minus 3 for the number of moles. If you have anything even slightly different, troubleshoot. You need to exactly match this number down to the last decimal place. 6.920035 E minus 3. We are similarly going to take pressure sensor data and use capstone to compute the average pressure between energy state B and C. So over here, enter the following number, 101,230, 101,230 pascals. The pressure at state B is the same as the pressure at state C because we're going to consider them to be the same, which is why we're going to use the average value. So right here equals that value. The value at B is the value at C, and we're just going to use an average for both of those pressure values. Enter. The volume at state B, again, was measured with a rotary motion sensor and was computed to be 1.5413 E minus 4 cubic meters. The temperature at state B is the same as the temperature at state A. So you can just do equals, click. Let's again calculate the number of moles with this data. It should be exactly the same as the number of moles calculated for energy state A, but there's going to be a little bit of difference because we are using experimental apparatus. So right here, you can just select this cell, take your mouse and select this lower right tab and drag it through energy state B, C, and D. Here's your next sanity check. For the number of moles at thermodynamic energy state B, you should have 6.781100 E minus 3. You need to match that exactly. It's not good enough to be pretty close. You have to exactly match that value. If you don't, troubleshoot. The pressure at thermostat C is the same as the pressure at thermostat B. And again, we're just going to use the average value for both of those pressure states. So you can just type in equals and back down to this value. The volume at state C was measured using a rotary motion sensor and was found to be 1.9768 E minus 4 cubic meters. Things heated up at state C. The temperature is 334.0126 Kelvin, and that number was captured via a temperature probe. Sanity check time. For the number of moles at energy state C, you should have exactly 7.206080 E minus 3. The pressure at thermodynamic energy state D is the same as it is at A, which again is why we're using the average. So let's just do equals and click PDA average. The pressure at D is the same as the pressure at A. Let's just use that average value. The volume at state D was collected using a rotary motion sensor and was found to be 2.0563 E minus 4 cubic meters. The temperature at state D was found to be the same as the temperature at state C. So ready, here goes, equals, and click on the temperature at state C. You can see the number of moles at energy state D should exactly equal 7.305358 E minus 3. Once again, if any of these numbers differ from what you have, go ahead and troubleshoot so that you exactly match everything on this screen. Let's calculate the average number of moles. Ready? Here goes. In this cell, type in NAVE colon, highlight the AVE, right click, format cells, subscript. Make Excel calculate the average. Don't use your calculator. Ready? In this cell, equals AVERAGE, left parenthesis, and take all of these N values for energy state A, B, C, D, close parenthesis, and you should have precisely 7.053143 E minus 3. Right now, this is the latest and greatest sanity check. We all have to have this number down to the 6th decimal place. Let's do a little bit of formatting right now. I'm going to highlight all of these cells right here. Center justify, middle justify. I'll take all of these cells right here and middle justify. In fact, I think I'll do a global select right now and choose middle justify. Let's right justify PBC average. Done. Let's right justify PDA average, which I think is already done. Let's right justify number of moles, the average number of moles, colon, done. Let's bold column headers, done. Let's bold row headers, done. Let's bold PBC average and PDA average and N average. Let's highlight this entire block because this is basically ideal gas law data. Select all of these cells, go under your fill option here, and I'm just going to fill it with maybe a color that looks like, that. And I think what I'll do is I'll take the header row, and make that look a little bit darker just to make sure we can set this column or set this area apart. So same color, but maybe a wee bit darker there. It looks like PDA average, for me at least, needs to be right justified. That looks better. So this is our latest and greatest ideal gas law information for states A, B, and C. You should have an exact match. Let me make a formatting adjustment. Check this out. I'm going to take this PVTN header, hold down the Shift key, left arrow through those 3 cells, and then hit merge and center. There. And then I'll call this PVTN space data. There. This is complete. This is a good looking ideal gas law data block. Now let's calculate the work done during this cycle. In this cell, you can just enter the header work. Underneath, let's calculate the work from A to B, colon, and let's do some formatting. Click on the AB, highlight the AB, right-click, format cells, subscript. Let's take advantage of copy and paste. Highlight the work done from state A to state B, Control C, and then let's just paste that 1, 2, 3 more times. Let's go up to this cell. Let's change it from work from A to B to work from B to C. This one should be changed to work from C to D. And this one I'm highlighting the cell and I'm hitting F2 and I'm using my arrow keys and changing it that way, DA. There. So very quickly we have the work performed during this cycle from state A to B, B to C, C to D, and then D to A. Okay, the work done from state A to state B is isothermal work. Well, we'll talk a lot more about the physics, but we can do the math right now. We know how to calculate isothermal work. Ready? You can type in equals PA times VA times natural log ln left parenthesis the volume at B, which is the final volume, divided by the volume at A, which was the initial volume, close parenthesis. You should have exactly negative 7.328598 E minus 1, precisely that number. The work performed between state B and C turns out to be isobaric work. We know how to do that using physics. Let's do that now in Excel. This is going to equal the average pressure between B and C, we have that right here, times the change in volume. So times left parenthesis, we end up at volume state C, which is right here, minus the volume at state B, close parenthesis, and you should have exactly 4.408567 E plus 00. That is your work done. This is why we like heat engines, because they do that work. Look at all that work that just happened. The work performed between state C and D is once again isothermal work. Let's do the mathematics for that here in Excel. Ready? Equals pressure at C times the pressure at B times the natural log ln left parenthesis. We ended up at state D, click, divided by state C, which is where we started from for this segment, close parenthesis, and you should have exactly 7.890170 E minus 1. That number exactly. That is some more thermodynamic work we got out of our engine. The work done from state D to A is isobaric contraction. We know how to do that using physics. Let's do that in Excel. Ready? Equals PDA average. It's basically P delta V. Here's the P. It's PDA average times parenthesis the volume where we ended up, our final volume, which is the volume for A, minus the initial volume for this process was the volume at D, close parenthesis, and that number should be precisely negative 4.364586 E plus 00. Now let's add up all of the work contributions that occurred over this cycle. Let's go ahead and merge these 3 cells. Highlight this cell right here, shift right arrow, and then select merge and center. In this merge cell, type the following: capital SW net equals WAB plus WBC plus WCD plus WDA space colon. Let me change this lowercase w to an uppercase W, and let me do some subscripting. Go ahead and subscript what I'm subscripting here. Change the font of this capital letter S to be that of symbol, and that's how you get the summation symbol. Let's go ahead and justify all of these labels here. There, looks good. Let's add up all of these work contributions in this cell equals sum parenthesis, and there's the addition of all work contributions. For this cell, here's our next big milestone check, 1.001380 E minus 1. Make sure you match that down to the 6th decimal place. We're going to calculate the net work done using a second approach and compare the two. For the second approach, we're going to integrate the area under the graph in Capstone. So in this cell, go ahead and type in WNet equals PDV space colon. Put your cursor in front of the P, click on Insert Symbol, specify the symbol font family, and for me, if I scroll all the way to the bottom of this symbol font family, I see the integral symbol. Click on it and insert. For the sake of this exercise, let's assume that Capstone calculated the area under the graph as 1.1313 E minus 1. I also need to subscript the NET, highlight, right click, format cells, subscript. One quick correction. This is redundant, so instead of calling this the sum of work net, just let's leave that as the sum of the work. Also, another correction, I need to change this from work subscript net to work subscript INT. Work done through integration. There. In this cell, let's compare the two results. Do a %diff of the summation of all work, which is what we get when we add up the 4 segments, versus the work done through the integration method, space colon. Go ahead and change the font of this S, capital S, to symbol. That makes it summation. That gives you the summation symbol. And let's subscript the INT. Let's right justify. And just for consistency, let's merge these cells, highlight, merge center, and merge these cells. Hold down the Shift key. This is my highlighted cell. Left arrow, merge and center. And again, just another right justify to keep things consistent. Right justify. There. The % difference calculation is as follows. You can enter equals 200 times one of the values minus the other value, close parenthesis, divided by left parenthesis, one of the values plus the other value, close parenthesis. And if we want to use absolute value because we just care about the magnitude, we really don't care if it's plus or minus, you can just add ABS parenthesis and then close the parenthesis. There. We should all have 1.218373 E plus 01 precisely. Now let's do a bit of fun formatting. I'm going to delete my work label from this location. I'm going to hit Control X, right arrow, Control V, and then I'm going to hold down the Shift key and left arrow, merge and center. I'm going to change the color of this work area. What's a good color? Maybe this color, maybe more colors, and select a nice light blue. That's probably too dark, so I will just go ahead and lighten that. And for the header, maybe I'll make the header darker just to make it stand out, make it easier to see this section as separate from the others, and bold the work label. I'll also highlight all of these sublabels and bold them as well. Okay, so we've collected PVT-N data using sensors. We've done a whole bunch of work calculations. Now let's figure out how much heat flowed into our system. So here I'm going to type in input heat. Let's merge this across these 3 cells. Merge and center, bold. Let's figure out the heat flow from QBC space colon subscript to BC. The process from state B to state C is an isobaric process, and we know how to calculate the heat flow for an isobaric process. It's Q equals N CP delta T. Let's do that via Excel. This simplifies down to equals 3.5 times the pressure between B and C, which is an isobaric process, and we're using that average value that you're going to get through Capstone, times left parenthesis the volume at C, which is right here, click, minus the volume at B, that was our initial state, close parenthesis, and you should get precisely 1.542998 E plus 1. This is the amount of heat that flowed into the system as it was going from state B to state C. Heat also flowed into the system from state C to D. I'm going to copy Control C, down arrow Control V, F2, and just change this from C to D. The heat flowing into the system is the same as the work performed between state C and state D. I'm going to hit equals and just click on this, the work done from state C to state D. And you should have 7.890170 E minus 01. Now I want to calculate the total amount of heat input. This is my investment. Qn equals QBC plus QCD space colon, and let's do the subscripting. Let's add up these two contributions, equals sum left parenthesis, select those two inputs, close parenthesis, and you should have 1.621900 E plus 01. This means 16.219 joules of energy was invested to your heat engine in the form of heat. Let's do some formatting. I'm going to right justify these labels. I'm going to bold them. I'm going to change this whole area to a different color. Maybe let's take a look at this color, maybe make it a little bit lighter. That looks good. Maybe make the header a little bit darker. And this section represents the total amount of heat that was invested to our heat engine. Now let's calculate Carnot efficiency, C-A-R-N-O-T efficiency. Let's go ahead and merge this across these three cells the way you see me doing. Bold. Let's specify the formula for Carnot efficiency. So type in lowercase h equals left parenthesis 1 minus TC divided by TH close parenthesis times 100 space colon. Change the font of lowercase h to symbol. So there's eta, Greek letter eta stands for efficiency. Let's subscript the C and the H. Let's use a bullet operator between the right parenthesis and the 100. Put your cursor between the right parenthesis and the 1. Click on Insert Symbol. Make sure your font is set to symbol. And if I scroll down a couple of clicks, I should see that bullet operator, which is right here. Insert. Close. There, I think I have a leading space, so let me get rid of that. Perfect. Right justify. Let's bold this label. Let's merge it across both of these cells. So highlight both cells, merge and center, and right justify again. And now let's calculate the Carnot efficiency. That equals left parenthesis 1 minus TC. TC was our cold temperature. That occurred at state A and state B, divided by the hot temperature that occurred at state C and state D, isothermal. Close parenthesis times 100. We should all have 1.714411 E plus 01. This means our Carnot efficiency is about 17%. Let's color code this section. Highlight these cells. Choose a color. I'm feeling green. There's green. That's too dark, so I'm going to go into the palette and lighten that up a bit. But I will make the header darker. There, that's Carnot efficiency. Last section, real efficiency, R-E-A-L space efficiency. Let's go ahead and merge that across these three cells. Let's bold it. Let's specify the expression for real efficiency. In this cell, type in lowercase h equals left parenthesis W-I-N-T divided by Q-N, right parenthesis, let's insert a bullet operator. Click Insert, Symbol, specify the symbol palette, and scroll until you see it and select it. Then specify 100%, space colon, and I can see I have some font weirdness going on. So I'm going to just click Home, specify font size, right justify, change the font for the H, lowercase h font is now changed to symbol. What else should I do? I should subscript the INT as usual, and the N. So this is saying real efficiency, eta, equals the amount of work we get, and we're going to use the work calculated by integration. W_INT means work calculated through integration, divided by our investment. Efficiency is what you want, divided by what you invest. I want work. I'm going to invest heat. That explains this formula. I think I have a space here I need to get rid of. I'm going to bold this. I'm going to merge these cells, right justify, and I'm going to specify my formula now. Efficiency equals left parenthesis work done, click, divided by investment heat, click, close parenthesis, times 100. We should all have this number, 6.975153 E minus 01. Let's color code this last section some different color, maybe orange, too dark. Go ahead and lighten that up. Make the header label a little bit darker. And you are done. Maybe one last formatting chore. Let's make all of these rows a bit higher. Things seem a little bit too compressed, a little bit too dense. Activate all of these cells. Click on Format Cells. Click on Format Row Height. And maybe let's just specify a row height of 20. That looks a little bit easier. Let's also adjust column width. Make sure every cell in your spreadsheet is activated. Click on Format, Column Width, and let's try 15 to see how that looks. That looks better. So again, things are more spread out, easier to look at. I think that's it. I think we are completely finished with this spreadsheet. One last time, look at every number. We should be in complete agreement down to the 6th decimal place. I can see a couple of adjustments here. I'm going to make sure these are center justified. This is center justified, and this is center justified. So just one last round of nitpicks. I think these should be center justified as well. And I think that looks good. Now all you need to do is take this spreadsheet and update these numbers, update your PVTN numbers, and everything else will be done for you automatically. You're just going to measure pressure using the pressure sensor, volume using the rotary motion sensor, T using temperature probes, and that's kind of it. There's quite a bit of capstone operations, but that's what we'll cover in class.